So here we have, let's see, what do we have? We have a speed skater that is coming to the end of a race and is coasting, but there's a frictional force acting on the skater, F, that has a magnitude minus K, which is constant, times M, the skater's mass, times the velocity of the skater squared. So there's no other forces acting on in the horizontal direction on the skater. So we just have this force here equals the mass times the acceleration of the skater in this direction. So we have ma equals minus kmv squared. A is just the time derivative of the velocity, so dv dt. We can see that our m's cancel out here. And so then we can separate variables and integrate to find our solution. So we wind up with the integral of dv of 1 over v squared dv from the initial velocity vi to the final velocity, or to the velocity that they are at some time t. And we'll call t equals 0 when they have velocity vi. So then we get minus k, which is constant, times the integral of dt. Just working out the integral here, and doing a little rearranging, we get 1 over v equals 1 over v, the initial velocity, plus k times time. Solving for v, we get that v equals the initial velocity divided by 1 plus the initial velocity times k times t. So we can see that indeed, as t increases, this velocity drops. And in fact, it actually theoretically never goes to 0, because it's proportional to v squared. So it's going to asymptote to 0, but actually never get there in this approximation of the situation.